Oh, hi. Welcome to part P of chapter 6 classes. In part A, we looked at section 6.1, 6.2, 6.3, and 6.4. And in the last part, we looked at ideal gas equation. Recall ideal gas law relates the volume over gas and pressure is directly proportional to the number of moles times the universal gas constant and temperature in Kelvin. Remember, pressure in ATM in atmospheres, you will need to change to atmospheres. Volume in liters, you have to change to liters always, the volume. And temperature in, this is temperature in Kelvin, because R equals 0.082006, and the unit for R is liters times atmospheres over mole times Kelvin. This is the units for R, and that's why you need to change what? You need to change the pressure to atmospheres because of the units of R. You need to change the volume to liters because of the units of R as constant, is the liter, and temperature has to be in Kelvin for that. We will use this equation in part P, section 6.5, to determine the molar volume of a gas, the density of a gas, and how to use the same equation to find the molar mass of a gas. I know you know how to determine the molar mass of a compound. Given the periodic table, you can determine the molar mass of a compound. But in this particular section, we will use ideal gas equation to find the molar masses of gases. 6.6, we look at the gases and partial pressures. We look at Dalton's law, partial pressure, and lastly in part P, we look at the stoichiometry, reaction involving gases. We'll also revisit the Paul's equation, what the coefficient in the Paul's equation mean in terms of reaction involving gases. So sit back, have your calculators, have your notebook, make sure you take notes, all right? So part B, 6.5, application of ideal gas equation or ideal gas law, which of this form, you need to know this equation. Remember the other three equations we covered: Charles' law, Paul's law, Avogadro's law. All right. Now in 6.5, before we look at how to determine the molar volume, density, and molar mass of gases or of a gas, there is a condition we call STP, standard temperature pressure. STP stands for standard temperature and pressure, and at STP, at standard temperature pressure, temperature is always to 73. Some others use to 73.15 K or 0 degrees Celsius. Note that at STP, temperature has to be 273.15 or 0 degrees Celsius. And pressure, okay? Pressure at standard temperature is 1.00 atm atmospheres. For concentration or molarity concentration, even though we're not going to look at this point, it's good to know condition at STP. Concentration or molarity equals 1.00 molar, the concentration. These are the condition at STP you need to know. Down the line, you'll be given a problem and you will see that at standard temperature pressure or just at STP, which you are expected to know, Now, what's STP stand for? So if you set the temperature to P273, pressure to P1 atmosphere, and you have one concentration of a solution at 1 molar, you are working at a standard temperature pressure. The volume occupied by 1 mole of a substance is called molar volume. And when we say at STP, this is the temperature. In the molar volume, all right, molar volume at STP is 22.4 liters. That means 1 mole of any gas. And in this case, when we're looking at gases, 1 mole of any gas occupies 22.4. We call this molar volume. The volume occupied by 1 mole of any gas. We call it that molar volume. At standard temperature pressure, 1 mole of any gas occupies 22.4 liters. We'll be using that down the line, the molar volume of a gas, that's the amount of space occupied by 1 mole of gas. Notice that it doesn't matter the type of gas you are working with. It doesn't really matter whether it is CO2, whether it is gaseous H2O, whether it is carbon monoxide, carbon dioxide, and so forth. All gases at STP occupy this volume. We call it molar volume. All right, when this diagram just highlight the fact that all gases at STP occupy the same space, the amount of space. We have 1 mole of helium at STP, 1 mole of xenon at STP, 1 mole of methane gas at standard temperature pressure. You notice that they all occupy the same space, the same amount of space at standard temperature pressure. It is not confined to only the 3 gases you see here. All other gases also occupy the same amount of space we call STP. Now, let's see, use the molar volume of gas at STP to determine the volume in liters occupied by 25.8 grams of krypton, 25.5 grams of krypton. So if I want to find the molar volume at STP, it is not this, but we need to change these two. In other words, remember 1 mole of krypton, all right, equals to 22.4 liters at standard temperature pressure. But in this amount given here, I don't think we have exact 1 mole. It will be a different amount of mole for krypton, krypton. So how are you going to find out this? You need to find, this is the solution, inside 25 of the amount given 25.8 grams of krypton, using the molar mass, atomic mass of krypton, you can use the periodic table. All right, let's see. I can just pull quick krypton periodic table. I'll give you, don't worry about Googling out during the quiz, but I will provide the periodic table during the exam. For now, I just want to look at the atomic mass of krypton, and we will look at. So I'm looking at krypton. It is 83.798, 83.798. So that's what we need to use. So it is 83. I need to minimize this to show you 83.798. I'm just going to minimize this. You see, this is my setup. 798 grams of krypton. And here is what? This is 1 mole of krypton. What I'm doing here is converting the given grams of krypton to moles of krypton using its atomic mass or molar mass of the periodic table. And then the conversion factor here is the definition at STP. You see this at standard temperature pressure, 1 mole of krypton occupies 22.4 liters of krypton. So that if you look at the unit cancellation, grams and grams will cancel, mole and mole will cancel, and this will be the volume at standard temperature pressure. So if I use my calculator, is double check 25.8 times 22.4 equals divided by 83.798. This is 6.89658 liters. This is more than what we need for in our final answer. 3 significant figures, 1, 2, 3. So I'm gonna stop there, and it's 6.90 liters with the correct number of significant figures. This is the amount of space occupied by 25.8 grams of krypton. Makes sense because 83.798 will occupy this because it's 1 mole. 1 mole of krypton should occupy 22, but we have 1 mole, which is 83 grams, but 25 grams will be way less than 83.79. So please look at problem number 59, 60 on page 257. It's on determination of molar volume occupied by a certain amount of gas, all right, certain amount of gas at standard temperature pressure. The point here is what you understand as far as STP is concerned. The rest will be much easy, just plug in the formula. Okay, let's see. Go back to the density equation. We learned previously that density of a substance is determined by taking the ratio of the mass over volume. Mass over volume, ratio of mass to volume of gas. And for gases, we express the units in grams per liter, So when you look at the mass here, this will be the molar volume. And volume here is the molar volume at standard temperature pressure, So if you look, for example, here, the density of helium and nitrogen at STP, please remember this, at standard temperature pressure, that means volume is 22.4. So if somebody asks you what is the density of carbon monoxide at STP, know that it's going to be the molar mass of a gas at the top, and this will be the molar volume. So here, unlike the regular equation for determining density, always at the top is the molar mass of what? Molar mass of any gas. And then this is the molar volume. This is the molar volume, which is equals to 22.4 liters. The rest you plug in should give you the density. 28.02, using the periodic table, 1 nitrogen, atomic mass for nitrogen is 14.01 grams per mole. And since we have two atoms of nitrogen, we multiply by this, and that is where we have 28. For helium, just of the periodic table. The 4 here is just of the periodic table to give you an idea of, how to determine the density at standard temperature pressure, standard temperature pressure. We can now use ideal gas equation. Using ideal gas equation, all right. I would say this is one method of determining the density of a gas, and then two here. Let me label it by saying density of gas using ideal gas law. Density equals to molar mass, all right, times pressure over universal gas constant times temperature in Kelvin Where where you don't need to derive this, this is just illustration on how to get the equation for density. So this is density. This is stand for density. Here is the gas constant. Temperature always. Temperature in Kelvin. Molar mass, and then this is the pressure in ATM, pressure in atmospheres. You have to know the unit, because when you get to the problem, by just looking at this equation, even if I give you in the exam and you don't know how to rearrange, express each one of them in the correct unit, you will not get the density, because this pressure could be in atmosphere. I mean, it could be in millimeter mercury, it could be in PSI, it could be in kilopascal, but you need to change to atmospheres. I gave you the conversion factor. Molar mass, you may be given that you need also to change the temperature into Kelvin. Other than that, the equation will just be useless in front of you in an exam if you forget to change. No one will tell you change the temperature to Kelvin, but you are expected to know that temperature has to be in Kelvin because of the universal gas constant here. It's the same as we looked at before, 0.08206. Remember the units, all right? Units here is liters times atmospheres over mole times Kelvin. That's why we are changing the units for R here is liters times atmosphere mole. That's why the temperature here has to be in Kelvin because of that. So that's the equation for finding the density of a gas using ideal gas equation, So here we can also manipulate the ideal gas equation to find the molar mass of a gas, Let's see an example, and just blow this up. You can look at an example on how to calculate the density of a gas using ideal gas equation. If you look at the problem, what is the density of carbon tetrachloride vapor at 740 torr? That is the unit for pressure, and 125 degrees Celsius. At the outset, there are some calculation you need to perform prior to plugging the equation for density. One, pressure has to be in atmospheres. Temperature has to be in Kelvin, all right? If you are not given the molar mass of your gas, you need to use the, chemical formula, naming of the compounds, writing of the correct formulas. You should be able to write the correct formula for this so that you use the periodic table to find the molar mass. Carbon tetrachloride. So at the outset, you'll see that this is what we need to have. Carbon tetrachloride is CCl4. This is not carbon, but chlorine tetrachloride. That means we have chlorines. We have that. At the outset, you need to have this molar density is pressure times atmospheres. Density equals to pressure in atmospheres times the molar mass over R, which is universal Charles constant times temperature in Kelvin. Let's see, you need to find or convert the pressure in atmospheres, in torrs to atmospheres. That's what's happening here. And this is what we need to use in our equation. Molar mass of carbon tetrachloride, we have 1 carbon and 4 chlorine. That's the molar mass. So pressure in atmospheres times the molar mass over universal Charles constant times temperature. Again, changing the temperature from 125 degrees Celsius, we have 298. And it turns out that the density of carbon tetrachloride is 4.42 grams per liter, 4.42 grams per liter. So please go back, look at how ideal gas equation has been used in determining the density. At the end of the semester, all right, you may have this equation on finding the density of a gas using ideal gas equation and using the regular equation for finding the density to find the density of a substance. Ask yourself, is this problem faced or you need to use ideal gas equation? Here, I don't have the volume, I don't have the mass, so mass over volume does not apply in this. But the temperature, the pressure, and the chemical formula for your compound, you are expected by now to translate the chemical formulas chemical names to formulas for you to find the molar mass. Please practice more on using the ideal gas equation to find the density. Let's see, learning check. Learning check here, let me minimize this. This will be our whiteboard on the right side. The density of ammonia in 4.2 liter container at 37 torrs and 4 to 5.0 degrees in grams per liter. At the outset, here solution, density equals to pressure times molar mass over R times T. Pressure is 837 TORR, change that to atmospheres using the conversion factor 760. No, 760 total. TORR 1. So what I'm doing here is I'm converting the pressure from torrs to atmospheres. Temperature is 45.0 degrees Celsius plus 273. So you need to know the temperature, all right? Changing the temperature to Kelvin. This is 318. 318.15. This is the temperature. And pressure is 1.1013 atmospheres. So this is what we need to plug in our equation for density, in our equation for density. So I get there, this will be Density equals to 1.1013 atmospheres. We have changed the pressure from torus to atmospheres, times the molar mass. Again, ammonia here, you should be able to write the correct formula for ammonia. It is NH3. Use the periodic table to find the molar mass, times 17.03 grams per molar of universal Cass constant 0.0821 liters times atmospheres over mole times Kelvin times the temperature 45.0 degrees Celsius. This is 318. This is what we changed that. Remember to change that 318. 318.15. 318.15. Crunching down the numbers, this will be 0.718 grams per liter, which is reasonable density of the gas. So if you look at what we are given here, we don't know the mass. We don't know the mass. We don't know the amount. So how do we proceed with determining its volume in grams per liter? Is by using ideal gas equation. Look at problem number 61 on page 57. This is it's a similar problem. You should have answers at the back of the text for question 61. Practice on how to use ideal gas equation to find the density of a gas. So we have looked at how to find the molar volume, how to find the density of a gas. Moving forward, we can also use ideal gas equation to find the molar mass of a gas. Recall, molar mass is given by mass over number of moles. If you know the mass and you know the number of moles you are given, you'll be able to find the molar mass. And remember, units for molar mass is grams per mole, grams per mole. We can use ideal gas equation to find the molar mass. This is how to find the molar mass using ideal gas equation to find or calculate the molar mass is given by molar mass M RT over PV, where M where M is, this is M, where M is the molar mass, is the mass in grams. This is mass in grams over gas. R is the universal gas constant. This is universal gas constant with a numerical value over mole times Kelvin. So you should know that temperature in T temperature in Kelvin, temperature in Kelvin. Because of the units of R, pressure has to be in atmospheres. Pressure in atmospheres, and the rest is just plugged in the equation to get the molar mass of a gas. So you want to find out the molar mass of a gas, all right? A sample, a 113 ml gas sample has a mass of 0.171 grams at a pressure of 745 millimeter mercury, temperature of 32 degrees Celsius. What is the molar mass? Clearly, this is a problem which calls for using ideal gas equation to find the molar mass. So I'll say mass equals to molar mass rather. This is molar mass, mass Phi. Remember what I explained here. This is the molar mass, this is the mass, this is the universal gas constant temperature. So we cannot plug in that. Remember, volume should be in liters, so we need to change that to liters as well. We're gonna change that to liters. Change that to volume to liters. So pressure (745). This is 745 millimeter mercury. 760 equals one atmosphere, which is equal 0.9803. So this is the pressure. What I've done is change the pressure to atmospheres because of the universal gas constant. Volume change to liters. Volume in liters is 0.113 liters. Temperature in Kelvin is 305. Yeah, so 305.15. So we have all the information we need, and of course the temperature. Kelvin. We need to find the molar, the density. Therefore, density is given by mass times temperature. I mean, universal gas constant times temperature over PV, which is pressure times volume. From what we are given, 0. So the mass is 0.171 grams times the universal gas constant 0.08206 liters times atmospheres over times Kelvin times universal temperature was 305.15. Over, all right, 0.9803 PV. So we have pressure times volume, which is 0.0. 0.08. Therefore, this should give you check 338.65 grams per grams per mole. Looking for molar mass per unit CH mass per mole. So that's how you use ideal gas equation to find the density of a sample of a gas. Problem number 63, 64, 65, and 66, and 66. On page 257, those are good practice on using ideal gas equation to find the molar mass of a compound, All right, we have looked at how to use ideal gas equation to find the volume, to find the density. All right. You should be able to determine those five identities, the molar mass, the density, all right, and the molar volume of gas at STP using ideal gas equation. Let's shift gears to something else. 6.6 is on Dalton's law of partial pressure. And when we talk about partial pressure, it is the pressure exerted by an individual gas sample in a mixture. Remember gases, all right, when we talk about gas, it may be a combination of one or two more gases. For example, dry air, let's see. When we talk about the dry air, it consists of nitrogen, oxygen, argon, carbon dioxide, and any other few trace amount or trace gases or gases in trace amount in the atmosphere. Pi nature, pi volume, percent by volume for each gas. Predominantly, we have nitrogen in the atmosphere. 75% of dry air is nitrogen. 21% oxygen, argon, 0.9, and carbon dioxide is 0.04 in the atmosphere. This is just an illustration that the dry air is a mixture of gases. It's not like one pure type of gas. In nature, we have a combination existing in nature. There are certain applications where the mixtures can be thought of one gas. Even though air is a mixture, we can measure the pressure, volume, and temperature of air as if it were pure substances. In other words, when we talk about the temperature of the day, we do not take into consideration the contribution by all these other gases, but we treat it as if it is a single entity. All right. So partial pressure, the pressure due to individual type of a gas in a gas mixture is called partial pressure. Pn. We can calculate using ideal gas equation. The partial pressure is given by the number of moles of that gas sample times the universal gas constant times temperature over volume. We can also use, apart from this equation, where N stands for partial pressure of gas type M, volume in liters, universal gas constant. However, we can also use this equation. According to Dalton's law of partial pressure, the sum of partial pressures of all gases in the mixture equal to the total pressure. That's according to Dalton's law of partial pressure. Please look at the term or the name. This is the name of a person who came up with the law, which is the law given here. You have seen before, and it states that the total pressure is a result of the summation. You'll see a different way of expressing that. Partial pressure for all gases. So we can use this equation if we are only given the partial pressure. This equation will work. If it doesn't, or if you are not given the partial pressure for individual, then you may need to use the equation, the ideal gas equation. Now, applying Dalton's law of partial pressure, a mixture of, see how we apply Dalton in calculating either partial pressure for a particular gas or total. So at the outset, we have 6.00 grams of oxygen gas. Remember, three significant figures. It's going to be three significant figures. 9.00 grams, three significant figures of methane is placed in 150 or 15, sorry, not 150. This is 15.0 liter vessel at 0 degrees Celsius. What's the partial pressure of each gas? Partial pressure for CO2, you need to find the number of moles. So look at how to proceed with finding the partial pressure. First of all, you need to find the number of moles of each gas, oxygen gas and methane gas. The molar mass here is 32. Mistake students make is assuming that it is oxygen atom using the 15 from the periodic table. Oxygen gas is diatomic, so therefore we need to use 32.00, and this is the number of moles of oxygen gas. Likewise for methane, using the periodic table, 1 carbon and 4 hydrogen is what we have. And these are the number of moles of each gas. So if we want to find now the partial pressure, look at our ideal gas equation is used. NBV over RT. N, which is the number of moles of oxygen times universal constant times temperature over volume. That's why we are given here volume in liters. If it was any other volume or other units, we will plug in that. So these are the partial pressures, and we were looking forward. What is the partial pressure of each gas? Yes, it was for each gas. So I'm going to take the number of moles for oxygen and using the ideal gas equation to find the partial pressure. And then if you are asked to find the sum partial pressure, that's what we are given. So here is another learning check, which you need to study as well. See how ideal gas equation has been used in determining the partial pressure. At 1.00 liter, there is a reason why we have two places of decimal. This is three significant figures. Our final answer should have three significant figures. So in a liter of vessel contains 0.215 moles of nitrogen gas. Remember, nitrogen gas diatomic. 0.0118 moles of hydrogen gas. Remember, all gases are diatomic at 25 degrees Celsius. Always remember to change the pressure to Kelvin, and partial pressure for each one of them, the number of moles. Pn and hydrogen. And you can be asked to find the total. So the essence is to find the pressure, which we can plug in the equation to get that. So Dalton's law of partial pressure is of this type. P total equals to summation of pressure 1, pressure 2, pressure 3, and so forth, depending on what you have. The ratio of partial pressure, a single gas contributes, and the total pressure is equal to mole fraction. So mole fraction is the number of moles of component A over total moles, or mole fraction is the total number of moles, or number of moles of substance or gas A over the total number of moles. We can calculate the partial pressure by taking the partial pressure of a gas times its mole fraction. A in this case is this is the mole fraction of gas A times the total partial pressure. That gives us the total mass, total pressure in a collection. We have 78 nitrogen. You will get the total pressure. Let's see, calculate the mole fraction of nitrogen monoxide. This is nitrogen monoxide in 10.00 liter gas cylinder at room temperature, which is 25 degrees Celsius, that contains 6.022 moles of nitrogen gas, and in which the total pressure is 14.75. So at the outset, you need to change the temperature to 250. You need to change the temperature to Kelvin. Change the temperature to Kelvin. And from here, these are the total number of moles. How do you know that? PV over RT give us the total number of moles. And this will be the number of moles from the mole fraction. Look at page 73. Problem 73 on page 258. It has a good question on finding the mole fraction. Mole fraction is the number of moles of component A over total number of moles or total number of moles in the container. Well, this is just an applying the pressure concept to real life situation where divers, when they dive at the bottom of the ocean, there is increase in pressure. There is increase in pressure for every 10-meter depth. There is an increase in pressure of about 1 atm. The other illustrates that. They always carry pressurized tanks of oxygen. Otherwise, lack of oxygen can lead to that. All right. Please read on pressure conversion. Lastly, let's see the stoichiometry revisited again. Remember stoichiometry quantitative relationship between the reagents and the product in a chemical reaction. In section 6.7, we will look at the reaction which involve gases. All right. At the outset, for stoichiometric purposes, to get the number of moles, PV over RT, rearranging ideal gas equation, or the volume could be obtained from the number of moles gas, number of moles times universal gas constant times temperature over the pressure. We can either find the moles or find the volume. Using dimensional analysis, we looked at before how to do mass to mass. Remember this? Just like in this flowchart, we can also use ideal gas equation to find the amount of gas A, get the moles of gas A, use the mole ratio in the balanced equation to find the amount of B in the mole ratio of the balanced equation. Then we can use ideal gas equation to find the mass of B substance, B in this case. Or calculating the required volume of gas. Remember, stoichiometry revisited, but this time we are looking at the reaction which involve gases. For example, here, carbon monoxide reacts with oxygen gas to produce carbon dioxide in the mole ratio of 2:1. For every 2 moles of carbon monoxide, 1 mole of oxygen is consumed to produce 2 moles of gaseous CO2. We can write down the conversion factor between the two. All right, depending on what you are looking for. It can be in milliliters of could be in milliliters of your cast sample, but we can use the stoichiometry to find out. For example, to produce how many liters of oxygen will be consumed if you have 65.8 ml of CO2. This is how much it will just be consumed. It will just be consumed. I know we are looked at the converting between grams and moles before using the molar mass of a compound, the stoichiometry between the two reagent. 1 mole of chlorine gas react with 2 moles of sodium, and then the number of moles we can use PV. Universal gas constant RT over B. This is the flow chart for following when calculating the reaction involving gases. Sodium peroxide, N2O2, is used to remove carbon dioxide from and add oxygen to the air supply in the spacecraft. So it works by reacting with CO2 in the air to produce sodium carbonate. You see, this is the sodium carbonate with the mole ratio of 2 to 2 to 2 to 1, right? What volume in liters of CO2 at standard temperature pressure will react with? So to react with a kilogram, remember a kilogram is 1,000. So what you need to do is change the given mass. See, what volume in liters of CO2 will react with? So we need to find the amount in moles. See, this is the amount in moles. We had 1 kg. Moles of carbon dioxide. So volume is given by using the universal gas constant PV nRT. This is N, this is universal gas constant over pressure. That's how you use ideal gas equation. Using combination of stoichiometry and ideal gas equation, we can also calculate the volume of gas that we expect to be produced, just stoichiometry revisited. Here is an example on reaction between, or decomposition rather, of sodium acid. We call this sodium acid. It is what is in your airbag, in the automobile airbag. They put sodium acid, which upon the impact, it will release nitrogen gas, which deploy and inflate the airbag. It's called sodium acid. And if you look at the equation, it is 2 to 2 to 1. So a typical driver side airbag contains about 50 grams of sodium acid. Determine the volume of nitrogen gas that will be generated by the decomposition of sodium acid at 2 It's decomposition of sodium acid at 85 degrees Celsius and 1 atmosphere. So this is an ideal gas equation. What we have is the mass, all right, and the balanced equation. Changing the moles of sodium acid, or determining the moles of sodium acid mass over molar mass. This is the number of moles of sodium acid in 50 grams. Is the amount of nitrogen using the stoichiometry in the balanced equation. For every 2, 3 are produced. Once we know the number of moles, we plug it in ideal gas equation to get the volume. 33.98, 33.98. Let's see, learning check here on, I'm gonna minimize this right here and see. The mole ratio between hydrogen gas and oxygen gas is 2 to 1. It is 2 to 1, 2 to 1. So how are we going to find out the mass? How many grams? Remember, we're looking at what? Grams. How many grams do we have at standard temperature pressure? Be careful with this. Standard temperature pressure, you need the volume. So solution for this, solution at STP, 1 mole of, you need to know this, 1 mole of H2O two grams of H2O. Therefore, what we are given here is converted volume of hydrogen gas using the mole ratio. If you have 1.2 for liters of hydrogen gas, we can use the mole ratio here that 2 moles and more, liters and liters. Up to this point, this will give us liters of hydrogen gas. .24 liters of A2. Therefore, once we know the liters, we multiply by what? 1.24, 1 mole of H2O occupied in 2.4 liters times 18 mole of H2O. So that mole of H2O, liters and liters will have 0.995. So if I look at 3 significant figures, 2, 3, so 0.998. How many grams? This is grams of H2O. Grams of H2O. Here we use the condition at STP and the mole ratio in the balanced equation. This is the mole ratio here. To find the mass of H2O produced. Look at 79, 80, 83, not 80, but 81, 83, 85, and 87 on page 257. 257. That marks the end of part P. I'll come back again for the last part in chapter 6. Please